what I've written here is energy that an object has represents the work that had to be done to get the object into that state. What do I mean by that? I've got here, I'm just calling these four objects 4 bags of lead shot. Now you might wonder why I'm using this example, but it just makes it easier when I relate it later on. So just imagine that these are 4 bags of lead shot, and this chap here has got to lift each one up onto the top of this shelf here. So he's got to go and pick that one up, put it up there, and put each one up in turn. Now, so I've written here, this chap has to pick up these bags of lead shot and place them on top of this shelf. So here's a picture of before he's done the activity, and here's a picture afterwards. Now you can see he's pretty tired there because he's lifted up all of these quite heavy bags of shot onto this shelf. In the action of lifting one of these bags, he's had to use up an amount of energy. Let's say this chap expends 5 joules of energy lifting each bag of lead shot onto the shelf. In the work he done to lift one of these bags up, the energy that he put into lifting this bag of lead shot was 5 joules. So we can just think of energy as the work he's done, and we've got a unit for that. We call work done, we give it the unit joules. So if he's spent 5 joules of energy, in his body, he's eaten food to give himself energy, and now you can see he's exhausted, so he's going to have to go off and get a meal or something to get those calories back into his body to give him those 5 joules that he's lost. So the 5 joules that he's lost in picking one of these up is now lifted up in the air against gravity, because that's how he uses energy, worked against gravity, and this bag of lead shot now has got 5 joules in the fact that if it falls off that shelf, or it's pushed off that shelf, those 5 joules that he's used to lift it up will be released, and basically they'll be released when that bag hits the floor and you get a bang or a dent on the floor. That's where that 5 joules will disappear. So the 5 joules that he used to put it up there will then be released. So that's what we mean by energy and how we can release it. So all of these balls here, there's 5 joules he used to pick that one up, 5 joules he used to get that one on the shelf, that one 5 joules, and that one 5 joules. So on this shelf we've got the potential of 20 joules of energy. So as each one of those lead shot balls, if they was to drop off that shelf, they'd all release 5 joules of energy, the amount that he put in. And you can imagine if they all dropped off at the same time, that would be 20 joules of energy that would be released quite quickly. So the other thing about energy, if it's released quickly, that's the definition of power, because power is really how quickly you release energy. So just read this again. So upon this shelf we have 5 joules per bag of shot. So that's the interesting unit. Now what we're saying is that on that shelf is 5 joules per each bag of lead shot. So that there, you can see I have 5 joules and I put a division sign on there per bag of shot. So that's quite interesting. Just remember that each of these is 5 joules per bag, per lead shot bag. Okay, so that's the concept. I just want you to get that concept now. He's lifted up each of those bags of lead shot, and they each cost him 5 joules to get them up there. So they've all got a height now. They've all got this potential energy of 5 joules that can be released when they drop. Okay, so that's the important thing to get from this one. So let's go on to the next sheet. Okay, so this sheet we're now going to define what voltage means, and I'm going to use that same analogy here now. But what we're going to do, we're going to say, let's say instead of lead shot, that each bag instead holds a coulomb of charge. So instead of there being lead shot, we can think of those as all being little units of charge, okay? And where a coulomb is an electrical unit representing a huge number of tiny charges. I can't remember the exact number of charges, but it's a huge number of charges. So we're going to say, instead of that being lead shot there, there all be little tiny units of charge in there, which in this total bag here is 1 coulomb, okay? So that's just to think of that now. So now we've got 5 joules of energy on that shelf for each bag which holds a coulomb. So we can say 5 joules per coulomb of energy now is on each of those bags, okay? So let's call this shelf a battery. So we can think of the height of this shelf as the plus terminal, if you like, and the floor of the shelf as the minus terminal, if you want. So we've got all of these bags here. They're all 5 5 joules for each coulomb that was put up there. Yeah, so we can say that if we was to release this coulomb of charge from each of these bags and they go down to the floor, we can say that every coulomb of charge that goes from the plus down to the minus loses 5 joules of energy. Yeah, so obviously that 5 joules that it took to get that coulomb on the shelf there is going to be released when we drop all the charges down to the bottom of the floor. So the losses of those 5 joules of energy are going to be in the heat of impact in this particular case. Okay, this is a very convoluted case, but I'm just using it as an analogy here to try and give you the idea of what voltage means. We've got a name of amount of energy per coulomb. We call it 1 volt. Okay, so our shelf can deliver, but our shelf here, this imaginary shelf we set up, we're saying that it can deliver 5 joules per coulomb. So what we're saying is 5 volts. So we're going to, this imaginary idea here, we're saying that each of these is equivalent to 5 volts. And that means 5 joules per coulomb that's released. So when that's released its coulomb, that's 5 joules that has gone. So we can call it 5 volts. We can say that desk setup there is a 5 volt battery, if you like. So our shelf can deliver 5 volts, 5 joules per each coulomb of charge that flows down there. So this is really just an analogy to give you an idea that voltage is really the amount of energy that's released per coulomb of charge that moves. I hope that makes sense. That's what voltage is, really. So I'm going to go into this a little bit more detail now to try and hammer this through. And this will introduce us to the concept of a voltage divider. So here I've produced this little analogy. So what I've got here is that same sack again. I'm just using one sack now. There's the shelf. There's the bottom of the floor here. I've designated that as a minus just so you can get an idea. It's similar to a battery really. And at the top there is the plus. I'm saying there that this whole sack, just like in the last diagram, that whole sack holds a coulomb. And we're releasing them at a steady rate through this pipe. Now this pipe, as you can see, it's got a wide section at the top, and then it narrows to a very small section, then it widens out to where it was there, the same amount, and then it narrows a little bit here. Now the narrowing here, I've tried to depict this, is twice as narrow as that narrowing. Now that narrowing of the pipe, I'm calling that resistance. These charges, is going to be harder to get them through that narrow pipe than through the thicker pipe. So there's a high resistance there to allowing those charges to move through. That's offering a higher resistance. Now this one is not. It's also offering a resistance, but it's not offering as much resistance. In fact, I'm going to say that this is 2 times the resistance of this. So if we say that's 1 resistance, that's 2 times the resistance. So in this sort of analogy, this sort of made up example, I've only got to make one assumption, and that is that all the energy is used up moving through the pipe. So I'm not going to say that all the energy now is delivered to the floor. I'm going to say they're going to lose all of those 5 joules for that coulomb that moves. It's all going to be used up in this resistance. Now, you might say, how is it used up in the resistance? Well, that's kind of like, you can think of that in everyday sense. You know, if you've got a foot pump or a bicycle pump, you know that when you push the air through a tiny hole, everything gets hot. That's because of the friction. You know, the air can't get through the hole quick enough, so everything gets hot, and that's all the little particles, all the little molecules banging against each other, and they cause heat. So that's exactly what's happening here. The charges are trying to be forced through a really small hole here, and so they'll generate a lot more heat than the less narrow restriction here. So that's this silly made up thing just to give you an idea about restriction and what resistances mean. So in the electrical sense, we're saying the same thing. Instead of using this bag here, we're just going to say 5 volts now. So we're going to say we got, for every coulomb that moves from there to there, 5 joules is going to be used up. That 5 joules is going to be used up by both this resistor and that resistor. So I'm going to say here, case 1, if these 2 restrictions here, or these 2 resistors, are the same value, then the 5 joules, how it's going to be distributed, half the amount of energy will be eaten up by that one, and half the amount of energy will be eaten up by that one. So you're going to get 2.5 joules eaten up by that one, and 2.5 joules eaten up by that one. And again, if this is just 1 ohm and that's 1 ohm, you get a massive current, so the things will probably catch fire, you know. But if that's 100 ohms and that's 100 ohms, then it won't catch fire. You know, you'll have a lower current or charge flow, if you like. So that's what that means. So when they're the same, the 5 joules will be broken up equally. You can get your voltmeter and put your plus on there and your minus on your earth. then you're measuring the voltage drop across this one here, across this RB, and you'll find it's 2.5 volts. If you take your terminal off the earth there and stick it there and stick the other one there, then you're measuring the voltage drop across this one. And if you do that experiment, you'll find that that's 2.5 volts as well. So that's case one. What about case two? Well, case two, what we're going to say is that RA is 2 times this. So if this is, say, 200 and that's 100, then we know that most of the energy is going to be eaten up by this one because it's got a higher restriction or higher resistance. If you do that as a ratio, then that's 2/3 the 5 joules per coulomb. So 2/3 the 5 joules coulomb gives you 3.3 volts. So if you put your meter across this one now, you're going to measure 3.3 volts or 3.33 recurring. And if you put your meter across this one, you're only going to get 1/3 of 5 joules per coulomb. That's going to give you 1.67 volts. If you do that, you'll see that's true. I recommend you do it. You know, you actually get yourself 5 volts at the top here and actually try that. Get yourself a 2K resistor and a 1K resistor. They won't get hot then. And then you'll find when you put your voltmeter across there, you'll get 2/3 of 5 volts. And when you put it across there, you'll get 1/3 of 5 volts. So you can see the same thing here. You know, your energy is going to be in proportion to the amount of restriction here. So that's really what a voltage divider does. It divides the voltage in two. I've written down a formula here that you can sort of use, and you might want to write this down somewhere in your notebook or something, but energy used by a given resistance. So if we want to find out the energy used by, say, RA, then all we've got to do, and I've said it in words just now, but all you've got to do if you want to write it in a formula form, you can just say the resistance of the given resistor, you put that on top, you've got a division sign here, so you put that one on top, so that in this example, let's say that's 1 and that's 2. Let's say that's 2 and that's 1, yeah? So say 2 ohms and 1 ohm. So we put the 2 at the top here. Then underneath we put the total resistance. Well, 2 and 1 gives you 3 units of resistance. So there'll be a 3 underneath and a 2 at the top. Just like I said, 2/3. Now the energy of the battery per coulomb, well, it's 5 joules per coulomb. Remember, 5 joules per coulomb is the same thing as saying 5 volts. But I want to make it clear that we're talking about energy that's released per coulomb. That's why I'm not saying volts here. I want you to understand that volts is joules per coulomb. That's important. Otherwise, you don't get an understanding of what voltage means, yeah? So what we're saying here is the resistance of the given resistor. In this case, we're going to say it's 2. And then underneath, total resistance, 2 and 1 is 3. So that's 2/3 times the 5. So it's 2/3 times 5, which I said before was 3.3 volts. So that's the case when that's 2 and that's 1. And the case when they're equal. So when R1 equals R2, you've got 1 on the top. 1 and 1 is 2. So it's a half of 5. Half of 5 is 2.5 volts. So there you go. So that's proved that. You can use this formula and think of other possibilities. What happens if you make this resistor really large, say about 10 megs, and that 10 ohms? We can see that all the energy is, you're almost going to get, if you put your voltmeter now across here, and that's really high, what do you think is going to happen? Most of the energy is going to be dropped across there, and hardly anything's going to drop across there. If you took that resistor away, and you got no current flowing at all, so the coulomb will never drop through, you'll measure 5 volts across the gap. That's the last sheet. So basically what I'm saying here is that a voltage divider really is an explanation of how voltage is distributed between two resistors in a circuit. And you might say, oh, that's a very simple circuit, but really you can break very complex circuits down into this arrangement of 2 resistors. And it's so common in electronics, is voltage dividers, that it's really important that you understand the concept of energy and the concept of voltage, and then you can understand what a voltage divider is. If you've got to this point and you don't understand it, don't worry, because it's quite hard to get this in your head, to be honest. What I'd suggest is do some Googling on this, and be careful when you get your information, because a lot of people don't understand it. Even people who try and explain this don't seem to explain it properly. I mean, Wikipedia's not too bad, but they seem to overcomplicate things. I don't know why. There are some good resources out there, you know. So that's it. I hope that's helpful. And the next video I'm going to do is I'm going to be using the voltage divider in one of the second Arduino tutorials. Subscribe and like if you like this, and I'll talk to you on the next one.